Okay, so we're going to try and go through a quick run through of other concepts in thermodynamics. Okay, so in the chat, if you want to ask questions, you ask it in the chat. Okay, boom, here we go. Okay. Okay, so we have a fixed mass of gas. We have some questions here. We have a fixed mass of gas undergoes a cycle of changes shown. Wx, y, z, w. Okay, so number one, a fixed mass of gas undergoes a cycle of changes shown, Wx, y, z, w. The shaded area represents the difference in magnitude between the amounts of work done during. Okay, so here's how it goes. So let's look at the question here. It's a graph of pressure against volume. It's a graph of pressure against volume. And what we know, if you remember correctly, is that the work done is the area under a pressure of volume graph, which is the integral of P dV, right? So if you look at the question carefully, if you zoom in, you see some arrows. We'll see an arrow here on this process going from Z to W, one from W to X. Okay? That being the case, then it's telling me that this line here, I'm sorry, oh. Right. So this here, those two processes there are processes where the gas is being compressed. The volume is decreasing, so going from left to right. In those two processes, the volume is decreasing like that. So those two processes, work is being done on the gas. In the other two processes now, let me see if I can change the color of this guy. Other two processes here. In those two processes, the gas is actually expanding. How I know that? Because the volume of the gas right, is going from left to right. Boom. Gas is expanding. So in these two processes here, the gas is expanding. So the work done will actually be the area under ZWX. So that area actually looks like that. So going from Z to W and then W to X, this is the total work done under the graph, going right onto the axis. That's the work done when the gas is compressed. That's work done on the gas. And you have to take away now, when the gas is actually expanding, so following the X, Y, Z, that process there, right? The work done in that case will be this area here. That's the work done when the gas expands. The work done when the gas was being compressed is all this area here. So the net work done will be the difference between those two. That area in red shaded minus area in orange shaded will give us this area here, that's shaded in blue. Right? So the answer really is quite simple. The answer really is quite simple. Right? So the shaded area represents the difference in magnitude between the amount of work done during compression, which is Z to X, which is Z to W and W to X, or Z, WX, so that's this one here, and between X, Y, Z. So X, Y, Z, you go from here all the way to here to here. That's the answer, D. Number two, the first law of thermodynamics is a statement of what? Conservation of energy, right? So that one is self-explanatory, conservation of energy. Number three, A small quantity of water is sealed into a strong metal container, was heated continuously to a temperature above that at which the last of the water evaporated. So it's like a pressure cooker, basically, right? So let's see what actually happens when I do that. Okay. All right, so there's mouth and pan across. So that question has a situation like this. You have a sealed vessel, and it's rigid, I believe. Yeah, a strong metal container. So when you see a strong metal container here, it means actually rigid. So the diagram for that looks something like sealed vessel, and you have water in the vessel, a little bit of water in the vessel, instead of room temperature, a little bit of water in the vessel. And then after the person ignites some heat on it, what happens, the gas begins to evaporate. So, of course, when you start up, there's pressure, there's some air inside of here, and the air will contain some water, and there are air molecules above in this space. As you begin to heat the gas, what tends to happen is that gas molecules begin to do what? Evaporate, because evaporation takes place at all temperatures. So gas molecules will leave the surface and enter the gaseous phase. So what will happen, at some time later, you'll have a situation like this. You'll have less water, for sure. Less water inside of there. But what we will have is more gas molecules, right, with an increased pressure. Now remember, for molecules to escape into the air above it, it must overcome the pressure of the gas. So in this phase here, it was obviously easier for the gas molecule to leave the surface and enter here because the pressure above it was less. Now, by the way, we have not reached boiling point as yet. Let's say this is 20 degrees Celsius. And let's say this is 30 degrees Celsius. In this particular situation, what we are seeing here is that for a gas molecule now to leave the water surface and enter inside of here is opposed by a greater pressure. So the pressure of the gas is getting bigger. And then again, at a higher temperature, right, let's say 80 degrees Celsius, you'll have far less water. Water would have gone into the gaseous phase, but what you'll have is a massive pressure above here. And that pressure acts to prevent gas molecules from the surface to enter in here. So you need more energy in this time than that time to escape into that phase. Okay? Now, if you notice, I have water in each of these cases here, and the pressure above here at any temperature is called the saturated vapor pressure. Right? Anyway, the long and short is when you reach the boiling point, it will all be gas. So I'll do it in a different color. When you reach the boiling point now, you'll all have all the liquid have been boiled off. Only gas inside of here, and the pressure will be immense. And if you continue to heat after that, the pressure is just going to get even more immense. Right? So right, they'll be climbing with the water more viciously, and the pressure is going to be greater. So the point is that there's a pressure all along as you need to overcome the pressure above the gas, and the pressure is increasing in the liquid phase. But in the gaseous phase, as you add the energy goes directly. Remember, you have to do two things. You have to what? Get the molecules enough energy in earlier phases where there's liquid to break free from the surrounding molecules and get into the vapor phase. So the increase in pressure is kind of slow, but it gets increasingly bigger. Here now, when you reach the gaseous phase, there's all gas, all energy goes, there's no bonds to be broken directly to the gas molecules. The gas molecules get the energy directly, and the pressure increases very quickly comparatively. So, if you look at the diagrams there, I have one diagram here. This one will not be correct. This one assumes the pressure remains the same as you heat in the liquid phase, and that's not the case. As you heat in the liquid phase, the pressure gets bigger and bigger. So this phase here is kind of what will happen in the liquid phase, but the pressure will remain constant after. So this is wrong. This one is saying the pressure remains constant in the liquid phase, and then when you have liquid in the tube and evaporation, and then here it increases only after boiling. Wrong. This one here seems to be more like what we're talking about. As you're adding heat, right? As you add heat, the pressure increases. So you add heat, the pressure increases. You add more heat, the pressure increases even further. And here you reach the gas phase, and the gas phase, when you add heat, you have a linear increase in pressure, which is what I say. So answer D. All right, number 4. Back to number 4 and see what we have for number 4. A heated piece of brass undergoes 3 processes involving change of energy. 1, P is lifted vertically through 2 meters. Q, it is heated from 15 degrees Celsius to 20 degrees Celsius. And R is accelerated from rest to 10 meters per second. And they give us, given that the specific heat capacity of brass is that, and G is that, the process range in order of increasing more energy change are, well, let's compare the 3 processes, right? The 3 processes is telling me, first of all, that P is lifted vertically by 2 meters. Energy to do that is what? Energy to do that is M times G by delta H. Q is heated from 15 to 20 degrees Celsius. Energy to do that was equal to M by C by delta theta. R accelerated from rest to 10 meters per second. That's change in kinetic energy. That'll be therefore a half M into V squared minus U squared, right? Half M squared, final kinetic energy, half mu squared, initial kinetic energy. Well, I know which one of these processes don't have to write the increases in energy change in ascending order, because they asked me to do what? To arrange in order of increasing energy change. Well, that's simple. Well, mg delta H, right? When you look at all these equations, you'll see a theta in all of them. All of them have m. So the m is the same for all of them, the same mass we're talking about, and therefore we'll say the magnitude therefore depends on the other part. So if you divide 12 by m, you'll get the energy per unit mass to accommodate that change. So you can compare that because the question never gave us any mass. So I have to see whether, the question is whether G, to know which one to write as the smallest, which one is the biggest and whatnot. What I have to do, I have to actually write, see whether, which is the biggest. So G delta H, I'll ask myself, is G delta H bigger than C delta theta and V squared minus U squared? Let's see, I have V squared minus U squared. Let's do the numbers. Well, G delta H is what? 10 meters per second squared, that's 10 by delta H is 2, 10 by 2, that's 20. That's magnitude of G delta H. This is, then C delta theta, C is what? Oh, they gave me C is 380. And delta theta is 1520 minus 15, 5. This is 380 times 5. Let's do a calculator and so if you get there. So 380 times 5, I think that'll be something like about 400 by 5, like 1900. 380, yeah, it's 1900. 1900, this one is 1900 joules per every kilogram. Right, that's 1900 there. And then a half V squared minus U squared, that's a half into the velocity. 10 is V, U is 0. Half 10 squared minus 0 squared. A half 10 squared, so it's 100, that is actually 50. So just biggest. Smallest, 20, that's number 1. Smallest. Next one is number, this is 2 here, 50, and then 1900 is the largest. So I think we could see clearly that the smallest is definitely P. So P is the second one is R, so it's P, R, Q. P, R, Q. That's our answer. All right, an immersion heater. Let's look at this one. An immersion heater takes time T1 seconds, so T is capital T is time. This is temperature of the mass M of a liquid from a temperature T1 to its normal temperature T2. Now, immersion heater is it's connected to it has a power source that powers it. And you can actually find the power by finding how much heat is produced in a certain time. So they're telling us now the heater takes time T1 seconds, so it's the temperature of mass M of a liquid from a temperature T1 to its boiling point T2. So it's a liquid, and just reaches boiling point, the sensible heat change, right? is supplied in that process. I can actually say energy to heat boiling liquid will be M, mass of the liquid, which is capital M. C is the specific capacity, and the temperature change is boiling point T2 minus T1. This is all in the liquid phase. Okay, as the energy. Now, that takes place in a time, it takes T1 seconds to reach that. So using capital T as time, which is not common. Use small t's as temperature and capital T is, but let's roll with the flow. So therefore, the power, or the rate at which power is supplied, delivers this amount of energy in capital T seconds. So it'll be MC T2 minus T1 all over capital T. That's the power of the heater. So what we want to get now, right, in a further time T2, but the heater is getting energy at the same power, a mass M of the liquid is vaporized. What they're actually saying is this. We start off in the liquid phase at a time, at a temperature T1, heat it up to reach boiling point at a temperature T2, and after when you add heat, this part is the latent heat of vaporization being undergone. That's temperature, this temperature against time. Right, so this first part takes T seconds. And the second part here, what's actually happening here is that liquid is going from the, molecules are going from the liquid phase into the vapor phase. So you're going directly to the vapor phase and here all evaporated. What they are saying is we just use some energy to go from here to here. And so far they're saying that the amount of liquid, a mass of liquid M is vaporized. So from here to here, M liquid is vaporized, and I suppose it takes a certain amount of time to do that. Okay? So what do they want us to find? Specific latent heat of vaporization. Okay, so let's read the question over one more time. An immersion heater takes time T1 to raise the temperature of a mass of liquid from a temperature small t1 to its normal boiling point T2. In a further time T2, so next period T2, a mass M of the liquid is vaporized. So this time from here to here, that time frame from here to here, that is T2. The time frame from here to here, so is T1. So very simple now. So I know the power now of the heater is this, as the power of the heater. And if I take the power and multiply by the time, power by time. All right, so we get the power. So let's see the power. The power is P. If I multiply that by the time I'm heating in the vaporizing phase, T2 is the amount of energy I supply, which is equal to M by specific latent heat of vaporization. So I want to get this value here, the specific latent heat of vaporization. So I say the power by T2 all over M will give me a specific latent heat of vaporization. So let's see how that works out. My power was what? The power was capital M by C by T2 minus T1 all on time T1 seconds. That's the power multiplied by the time for the second one, which is T2 all over M, so M come on the bottom, small m, by, yeah, that's it. That's it. Power as the power we got from the sensible heat, multiplied by the time, A energy divided by the mass. So PT over mass. This is supposed to be, yeah, So, as you long and short of the answer, which one has that answer? MC T2 minus T1, T2 on T1. B is the answer there. Right? Again, it's really simple. To get the power that the heater is supplying, you can get it from the final amount of energy supplied to per unit time, and you get it from the sensible heat region. Right? You know, in T1 seconds, MC delta theta is the energy provided. We get MC delta theta by first time, you get the power. That's what we have here. Sensible heat. Then the latent heat, in the second phase, that power is left for T2 seconds. So power by T2, this is capital T2 here. Power by capital T2 will be energy supplied in vaporizing M kilograms, which is, and the energy to vaporize is M by LV. That's the, so that power by time all over the mass will give us LV. Right? So this is your power. Your time is T2. This is your power. And this is your mass. Vaporized. That's P, T on N. All right, number 6. Number 6. All right, number 6. Let's see what we do that one. Specifically, relating to vaporization of water 20 degrees Celsius is greater than the value at 100 degrees Celsius. Why is that? Well, simply put, energy, you can arrive at a different thermodynamic state by different means, but the energy from one state to the other state is the same. So what we're saying is that to go from, okay, okay, what latent heat does? Latent heat, you have to overcome the attractive forces in the phase in which you're in, and then you have to expand against atmospheric pressure. What the question is saying is, so the energy for latent heat does what? It breaks bonds first within the phase, and after that, you must do what? Expand against atmospheric pressure. And it also push back the pressure of the atmosphere on the surface to get into the vapor phase. Expand against atmospheric pressure. Now they're actually comparing the specific latent vaporization at 20 degrees Celsius and the to that at 100 degrees Celsius. Because it made no other reference to pressure, assuming the pressure is the same. So energy to expand against pressure will be the same in both cases. Right? So I'm saying this at 20 degrees Celsius is greater than latent heat at 100 degrees Celsius. Here, you have to break bonds again and expand against atmospheric pressure. So what's the difference? Now, atmospheric pressure is constant in both cases. So energy to do this is the same. Right? So then the energy to break bonds is where the difference must be made. So I can say, okay, let's get the answers. A, the specific latent heat of 20 degrees Celsius includes the energy necessary to raise the temperature of 1 kilogram of water from 20 to 100 degrees Celsius. That actually is kind of true. B, the more work must be done in expanding the water vapor against atmospheric pressure 20 degrees Celsius than 100 degrees Celsius. No, this work component is the same in both cases. Let's look at C. The molecules in liquid are more tightly bound to one another at 20 degrees Celsius and 100 degrees Celsius. That is true, because in heating from 20 to 100 degrees Celsius, it has spent energy breaking these bonds. So what is differentiated to is actually going to be this. breaking bonds, right? The energy to do that. And this one is bigger. So I think C will be our answer there. I'll put C. Right? Molecules are more tightly bound to one another 20 degrees Celsius and 100 degrees Celsius. As many atmospheric pressure as you see. Okay? Let's see. Let's look at another one. Boy, oh boy, oh boy. Where are we? Where are we? Let me see another question here. Error. Okay, so let's see. Let's see. All right, so let's see what we're seeing here now. And let's the questions here, so we could figure out these. All right, 7, in determining the specific capacity of a liquid using the constant flow method. The experiment is normally repeated so that heat loss from the flow tube may be eliminated in the calculation. If the inlet temperature and room temperature are unchanged, which one of the following quantities must also be the same in the two experiments? And they give us these 4 things to look at. Okay, so let's see. All right, so let's see. All working for that. So what we do, we have water going through a tube, and we allow it to reach steady state. So the rate at which you supply heat is equal to the rate at which heat is taken out of the system. So I supply electrical energy in via a heater, which is equal to the power by time, or is equal to V by I by T, right? Electrical energy. Water is coming in at a certain temperature, say theta 1. As the electrical heated, its temperature rises until it leaves at a different temperature, say theta 2. Now, what the question is saying is that when you're using the constant flow method, okay, we ensure that steady state is reached. So what actually happens is that the temperatures inside at every point remains constant, but not the same. So the temperature at this point, as the water is coming through, it comes through pretty cold. So I use it comes through at room temperature. And if you use the heater, it starts to heat up. Right, so it starts to heat up. And then it's a little hotter. And then it gets hot. I use red for hot. So by the time it leaves hot, leaves the heater, no more heating taking place, it leaves at that temperature. So what they're saying is this is the room temperature, water enters at room temperature here. And it gradually heats up and leaves at this temperature theta exit. And this is at steady state. Now we have heat losses taking place. And heat losses take place through the sides of there, like that, heat losses take place. What we are saying is that the rate at which energy is supplied, which is power by time, you can adjust the power of the heater, power by time, is equal to the rate at which the mass flow rate of water is m by c by theta exit minus theta the room, basically, where the temperature which water enters, plus your losses h. These are rates. I'm sorry, that's power by time. It's not a rate. Power, rate of supply energy is equal to the mass flow rate, is a rate, by C by the change in temperature plus H. All they're saying is that you're doing this twice. To make sure the heat losses are the same, these two temperatures have to remain the same. So this is fixed, and this is fixed. Okay? And if the temperature is fixed, I said this will be fixed. So all three of these are constant. Okay? Now what I'll do, I'll run over the experiment with a different power, but a different mass flow rate. So this could vary, a mass flow rate could vary, and your power will have to vary, right? So it's like water coming inside of here at a cool temperature about a certain rate. And you have a heater on. While the heater is on, the water will absorb energy until it leaves at a higher temperature. It's like this is like a water heater. If I increase the water flow rate to a higher rate and I have the same energy being supplied, then the water would not get as hot as it was in the first case. So in order to get the water to be just as hot, if I had to increase the energy of the heater so at a greater rate, so that you can actually get the water to come to the same temperature it was before. So it's like taking a bath at home. If you have your shower heater on and the water is coming at a certain temperature, at a certain rate, the heater will heat it up by a certain amount. So you get a certain amount of comfort. Let's assume the water all of a sudden, you increase the rate, the pressure of the water increases, and water will be coming through fast, and the same heat will heat the water up with the same exit temperature. So if you want the same exit temperature, what you have to do is to increase the power. Put the heater in a higher setting. Put the heater in a higher setting, you could probably get the exit temperature up to the same value. Repeat one more time. Okay, let's think about a typical shower heater at home. I hope you all have shower heaters at home. You know, if the water is flowing through fast in a particular power setting, the exit temperature will be hot, low. If it's flowing through very slowly, then the water tends to get hotter for that same power setting. So what we're saying is that we're comparing what we want when the same temperature exit. So when you're bathing, you want the water to be a certain temperature. Let's assume that the water pressure was low. Right? The water tends to get hot. Let's say the pressure increases and the water flows through faster. What you'll have to do now is the water will tend to get cool. So you have to get the same temperature. You have to actually increase the power system on the heater. That's what we're saying. So we want the temperatures to be the same. So if the water flow rate increases, to get the same temperature, the pressure must increase. That's what we're doing. We're doing two runs of that. So you have two pressures. We have P1 is equal to mass flow rate 1 by C by theta exit minus theta entry or room or whatever, plus same heat loss. All this is constant. Then you have P2, if the mass flow rate goes to a bigger value, M2 dot C theta exit minus theta room, then P2 be the power that brings it to the same temperature. And you have the same heat loss because the body temperatures are the same. So if you subtract the two equations, what you will get? You will get P2 minus P1 is equal to, these two terms are the same, with the exception of these two here. That'll be M2, that'll be M2 minus M1 of C by theta exit minus theta room, and H prime minus H prime, same heat loss is going to be 0. And therefore C will be equal to P2 minus P1 all over mass flow rate M2 minus M1 by theta exit minus theta entry. Right? That's basically what happened. Entry is room temperature. So to get C, you need to change with the power and the mass flow rate. So that's what the question is asking us. Number 7, let's go back. Right? What must be the same? If the inlet temperature and room temperature are unchanged, which of the following quantities must also be the same in the two experiments? The power, The mass flow rate, let's see. You want to get C. You want to get specific capacity. Okay, so electrical power input unchanged. Which one of the following quantities must also be the same? The power cannot be the same, so A is out. A is out for sure. You have a different power at a different fluid to get the same exit temperature. Rate of fluid flow. No, you can't have the same heat flow. That's wrong. You have the same heat flow, you wouldn't get two separate equations to cancel the heat loss. That's wrong. The period of collection of the liquid. Now, you're collecting the liquid just to get the mass flow rate. Now, you have two different mass. The outlet temperature is supposed to be the same. Now, if you collect the mass flow rate has to be different. Right? So I think it could be the mass flow has to be the mass of the liquid collected will be different for sure. And the answer B C, the period of collection of the liquid. Okay? To get the mass rate to be different, if you collect for the same time and two different mass rates, you will collect two different masses. So the answer will be C there. Let me just double check to make sure that is the answer. Can't be anything else. No. Oh gosh, no. The answer has to be D. Because I said that if the inlet temperature and the room temperature are unchanged, which one of the following quantities must also be the same? The outlet temperature, we said that. We said that must be the same. Okay, let's just go across and take a look. Right, in order to compare, okay, right, so we said in order to compare, all these must be the same. This is the inlet temperature, exit temperatures must be the same, right? That's how we're able to actually write this as, these two are the same. This is what different. Those are two things that are different. This is M1 of this, all this is the same. This is M2 of all of this. So you have M2 minus M1 of all of that. Okay, so yeah. Now let me see. Let me see which one now.